Good evening everyone, myself Gautam Sharma. I welcome you all in a Sapience Education. So today I am going to discuss about the NCERT solution for the class 12 physics, and the topic you know very well, electromagnetic induction. So first of all, we will start solving problem from question number 6.1. So first of all, read the question carefully so that you can understand, that is, predict the direction of the induced current in a situation described below. So produced of the direction of the induced current. So first of all, you need to know that what is Lenz law. As per Lenz law, direction of the current created. See basically what happens if you know the concept. So flux will change. So what will happen? It will create a current in the circuit. Now as per Lenz law, what exactly happens? That the creation of the current or the direction of current in a such a way that it will oppose the cause. So who is responsible for the creation of current in this one? So definitely movement of this one. Now definitely current will produced in this circuit in such a way that it will oppose. So when it will oppose, when this will behave as a south pole, when this will behave as a south pole. So let us check it. If it will behave as a south pole, if it will behave as a south pole. So the direction of current itself is from like this. You can see, observe it. Direction of current is like this. So the direction of current is from PQ PQRP like this, or QRP like this, whatever you can write. So this will be the direction of current. Now the thing is that, let's check part B. Now part B is that when it is approaching near, so it is south, so definitely it will also behave as a south pole. So if it will behave as a south pole, means, see, this side it will behave as a north pole. So since if you observe it, so current is like this. See, current is like this, current is like this. So current is going like this, right? So current is going like this. So from here we can say that this is from QPR, QPR, right? So this way we can see that. Now this one, so this is C here. This is going in this direction. Now this side will behave either south pole or north pole. So attract, see, when when this magnet starts moving in this direction or start moving this direction, so what happens, it will try to attract. So if it will try to attract, it means that this direction will behave as a south. So definitely this direction will behave as a north. So you know the rules how to find the direction of the current. So if it will behave as a north, so what will be the direction? Let us check it again. If it let us suppose it behaves as a north, so it means that the current direction is from this one, this one, this one, and this one. So this is y z x or x y z, whatever, y z x, x y z, right? Y z x. So from y to z, z to x. I hope you have understood this one. Let's go for next one. So next one is this one, right? Now it is saying that this switched in on, so what will happen? This is positive terminal, so current is going like this, and it is creating a current like this. So if it is creating a current like this, so what will happen? What will happen? The behavior of this loop will be, let us check it. So behavior of this loop will be like this. Then only it will match. So it will act as a south pole. So the current induced in this circuit will be in such a way that it will oppose. So it will oppose means it should also act as a south pole. So this is the case. So it means here the current will flow from Z, Y, and X. Got it? Now this one. Again, if you see this one, so this is the case. When switch is on, so this is the case, right? So this will behave as a north pole, right? So if this will behave as a north pole, so this side also it should behave as a north pole so that it can repel each other and it will oppose the motion, oppose the cows. So again it is XYZ. XYZ. So this is the way you can solve it. I hope you have understood this one. Now this one, tapping. A key is released. So what will happen? When key is released, so current is moving like this. So if current is moving like this, so it will behave as a north pole. So it should behave as a south pole. So that no, it should also behave as a north pole. So that they will repel. Always try to oppose. This is the Lenz law. So this will behave as a south pole. South pole, right? So if it is behaving like a south pole, so what will happen? It is coming like this, current is coming like this. So this will be Y R X. Now this is C. This is the current decreasing at a steady rate. So what will be the direction of current? So definitely current decreasing of current does not affect this one. Why? Because both are perpendicular. So there is a no impact. So no current induced. So I hope you have understood this one. Now let's go for this one. Now this one is 6.2. They are saying that use Lenz laws to determine the direction of the induced current in the situation described by this one. A wire of a irregular shape turning into a circular shape. Now see, it's the wire, but it start turning in a circular shape, right? So when turning in a circular shape, so what will happen? It will change the flux. So it means flux is increasing. Now what will happen if there is an increase in a flux? So what will happen? It will create a current in such a way that it will try to decrease the flux, right? It will try to decrease the flux. So when, how it will try to decrease the flux? By creating a magnetic field. In which direction? So if magnetic field is going inside, so what will happen? It will try to create a magnetic field in such a way that it will try to decrease this. So how this will be possible? That is, magnetic field is coming outside. So if you use right hand thumb rule, so what will happen? You will see that the current should go like this. Then only what will happen? It will create a magnetic field which is coming out, so that it can reduce the impact of the magnetic field. So finally the direction of the current will be from ADBC. So our solution for this one will be ADCB. So this is the direction. So I hope you have understood this. Now the second part of this question is that, just read this: a circular loop being deformed in a narrow straight line. So this is the circular loop and it has been deformed in the circular loop. So what actually happens here? What actually happens that EMF is equal to minus d phi by dt. Now what happens? Flux is decreasing, so it should oppose. So when when it has been, the size is decreasing, so what will happen? The direction of current should be in such a way that it should increase the magnetic field. Increase the magnetic field means what happens? So see here, this is the magnetic field. It means dot means magnetic field lines are coming out. So current should be produced in such a way that magnetic field lines should come out, right? Magnetic field lines should come out. So it should be only possible when the direction is anti-clockwise direction. So if you use right hand thumb rule, so you will be able to understand that it should be anti-clockwise. So the solution for this answer will be D, C, B, A, right? So I hope you have understood this one. So finally we have done 6.2. Now let's go for 6.3 question. Now before solving question, first of all read the question, pause the video and read the question properly so that you can understand it. Okay, I hope you all have read this question, so let's go for it now. A long solenoid with 15 turns, how many turns per centimeter? 15 turns per centimeter. So solenoid, I hope you have understood this solenoid. So let us suppose this is a solenoid. This is a solenoid like this, okay? This is a solenoid, right? And it has how many turns? So 15 turns per centimeter. So number of turns of solenoid is number of turns of solenoid, that is equal to how much? It will be 15 turns per centimeter. So you take it standard. So it will be how much? 1500 turns per meter. So it is the standard one. So use meters in spite of this. So that is equal to 1500 we have, right? Now area. So the area of this one is how much? Area of the circular loop cross section area is equal to 2 centimeter square. So we can write here 2 into 10 to the power minus 4 centimeter square, right? So this is meter square, right? Now I changes, see here current at the second line or third line, you can see that current changes from 2 to 4 in a time period of 0.1 second. So what they have provided you, current change in a current. So let us put here change in current, di will be how much? 4 minus 2, that is equal to 2 ampere, and the time, that is change in a time for this one, is equal to 0.1 second. Got it? Now induced EMF, we need to find a induced EMF. So induced EMF, that is E is equal to d phi by dt, right? E is equal to d phi by dt. Now just to solve this one, d phi. So first of all tell me how to find phi, change in a flux. So flux means we know that d, that is magnetic field strength into area. So is there, what they have provided you, magnetic field strength they have provided you or not? Okay, so magnetic field strength they have not provided you, but we know that the magnetic field strength for the solenoid is mu naught into Ni, right? So from here we can say that magnetic field flux is equal to mu naught N I into A. So this is phi, right? Now if you want to find d phi by dt, so how we will use d phi by dt? So this will be how much? D phi by dt is equal to how much? Mu naught N A d I by dt. Got it? So mu naught is how much? So mu naught is equal to 4 pi into 10 to the power minus 7. We have already discussed. Into number of turns is 1500 into area of cross section is 2 into 10 to the power minus 4. Now the thing is that what is di? Di change in current is 2, by change in time is 0.1. So overall when you are calculating, so what will be the final value? So final value will be 7.54 into 10 to the power minus 6 volt. So I hope you understood this one. So, and this itself is the EMF, right? So I hope you have understood this one. Let's go for next one. A rectangular wire loop of a side 8 centimeter and 2 centimeter with a small cut moving region of a uniform magnetic field of a magnitude of 0.3 Tesla directed normal to the loop. What is the EMF developed across the cut if the velocity of the loop is 1 centimeter per second in a direction of the normal to the longer side and a shorter side? So let us suppose, let us draw first of all what they have given. They have given that there is a circular loop, and there may be anywhere, there may be a a small opening like this, right? Okay, let it be. Don't worry about that too much. And there is a magnetic field. There is a magnetic field which is perpendicular to this one. So let us suppose this is a magnetic field which is perpendicular to this loop, right? Perpendicular to this loop, right? What they have given you. So first of all, write this one so that we can get an insight. So magnetic field, they have given you G 0.3 Tesla, right? And the velocity they have given you 1 centimeter per second, right? 1 centimeter per second. So we can use it as a 0.01 meter per second is the velocity. So this is the best one. Got it? So I hope you have understood this one. Now the length is how much? The length they have provided you as L and width you as B, right? Now they have provided you length as 8 centimeter and breadth is 2 centimeter, right? Now they are telling that if they are moving, see, first case you need to understand. Case you need to understand that the direction, see here, what is the EMF developed across the cut if the velocity of the loop is 1 centimeter per second in a direction normal to the longer side. So normal side means if you are going in this direction, so we are this is the case A. So we will talk about case A. So case A, right? Case A. So which one will participate for change in flux? So definitely this one will this line will participate in the change in flux, right? So what we need to do, we need to find a EMF, right? And EMF is induced. So EMF induced will be how much? So we know that EMF is equal to B into L into V. So magnetic field strength is how much? 0.3 into length is how much? Length is 8 centimeter. So this will be 0.08 meter and the velocity is 0.01. So finally we will get values. So if you try to calculate it, so how much value you will get? Hmm. So let us calculate. Pause the video and try to calculate it. So you will get EMF. EMF is equal to EMF is equal to 0.6. Sorry, or 8 3 is 24. No. So how it will be 0. So this will be 2.4 into 10 to the power minus 4. So this is the EMF. Now the time taken to travel along width. So time taken to travel. See, how far long does the induced voltage last in each case? That is time taken to travel is till see here. The thing is that when this coil will move, right? So when this coil will move, so as soon as this width will get see as soon as this width will get ended up, so it means that the time got finished or the creation of the EMF will be finished, right? So from here what we need to do, time taken to travel. So how much time it should be take? So time travel taken to travel, that is t is equal to distance divided by velocity. So distance is how much? So definitely distance travel when we are moving in this direction, so this amount of distance we have to take, right? That is this amount of distance is only travel, right? The magnetic field said that is we need to take 0.02 divided by 0.01. So this will be how much? Velocity. So this will be how much? 2 second. So this is case A. Now there is another case, that is case B. So case B, case B length, case B what to do? Again we need to find EMF. So EMF is equal to B, but the length. So when we are traveling in this direction, so the length of the travel will be how much? So when we are traveling in this direction, so this length is responsible for the creation of the EMF. So this, that is B, length will be used as a B width and to velocity. So B, how much we have? 0.3 into width is how much? 0.2 into velocity is how much? 0.02, right? Sorry, 0.01. So when you multiply it, so what you are going to get? So you will get 0.6 into 10 to the power minus 4 volt. So this is the EMF. Now the case is that, see, when it is moving, so the time taken, so time taken will be how much? Time taken, see, EMF will be only created till this wire will move in this direction. So for how much time it will move? So this length, so length is given, velocity is given, so time taken will be how much? Length by velocity. So length of the length is how much? Length will be 0.08 and velocity is 0.01. So finally we are getting as how much? 8 second, right? 8 seconds. So I hope you have understood this one, and so in this way you can solve this one. So let's go for next question. One meter long metallic rod is rotated with an angular velocity of 400 meter per second. So there is a one rod, and it has, let us suppose this is a rod, and this has having a length, and it has been rotated with the angular velocity of 400 radian per second about an axis, right? This is the axis, central axis. So it has been, or we can say that there is a rod, it has been rotated like this or anywhere, right? So I hope you have understood this condition about the axis normal to the rod passing the one end. Now the thing is that what they are telling, the other end of the rod is connected with the circular metallic ring. A constant uniform magnetic field of 0.5 Tesla is parallel to the axis everywhere. Calculate the EMF developed. So I hope you have not understood or not. Let's try to make you understand. So there is a circular ring like structure, and it has some wire, and there is a rod which will move with a some angular velocity, and this rod is having a length, this one, and this, when this rod will be there, so there is a magnetic field like this, so it will cut the magnetic field, so it will, there will be a change in a flux, and whenever a change in a flux will happen in this one, so what will happen? It will create a EMF. We need to find the EMF. Let us see what they have provided you. First of all, length of the rod they have provided you as 1 meter, and after that angular velocity, that is omega, they have provided you 400 radian per second, rate per second, right? About an axis normal to the rod of the passing through it ends. The other end of the rod is connected with the circular metallic ring, a constant uniform magnetic field, that is B is equal to 0.5 Tesla they have provided you. Calculate the EMF developed. So EMF is equal to how much we need to find out, right? So this is very important. So you need to understand how to solve this type of problem. First of all, tell me, if you talk about the linear velocity, so at this point, linear velocity at this end point will be 0. But at this point, at the end point, linear velocity v is equal to I into omega will be there, right? Got it? Or L, or L omega, not I omega. Length, we are considering length, so this will be length into omega. So average velocity will be how much? See, at one end there is a 0 velocity, and at other end there is a L omega velocity. So average linear velocity will be how much? Average linear velocity is Average linear velocity is equal to how much? This will be I omega plus 0 divided by 2. So this will be I omega by 2, right? Now EMF developed between the center of the rings we need to find out, right? So we have got the velocity now, average velocity, because one side there is a zero velocity and another side there is a I omega or R omega velocity. So how to find that? So we have done just averaging so that we can get the best result. So EMF will be equal to magnetic field into length into velocity. So this will be how much? B into why I am writing I omega, so it will be L omega, right? So B into L omega divided by 2. So this will be B L square omega by 2. So this is the derivation also. If you remember this formula, so you can directly find out the answer. So B is how much? 0.5 Tesla into L square means 1 square into omega is 400 divided by 2. So finally we are getting EMF as if you calculate it, or if you want to calculate it, just calculate it in a proper way. So this will be how much? 100 volt approx. So I hope you have understood this question. So let's go for next question. Now next question is our 6.6. So let's read the question first of all. A horizontal straight wire of 10 meter long extending from east to west is falling with a speed of 5 meter per second at a right angle to the horizontal component, and the earth's magnetic field is this one. What is the instantaneous value of the EMF induced in the wire? So let us suppose there is a wire and it is just crossing a magnetic field, so it will create or it will induce an EMF. We need to find the EMF. So length, they have given length is equal to how much? 10 meter. Velocity is how much? 5 meter per second. And magnetic field, they have provided you B, that is B is equal to 0.3 into 10 to the power minus 4 Weber per meter square. Now EMF induced will be how much? EMF is equal to B LV, we know this one, so this we should do this one. 0.3 into 10 to the power minus 4 into 5 into 10, so this will be 1.5 into 10 to the power minus 3 volt. So this is the EMF which has been produced in this wire. Now what the part they are asking, what second part, what is the direction of the EMF? So I hope you have understood the scenario. If you have not understood this scenario, let us see. A horizontal straight wire of 10 meter long extending from east to west. So if you observe this one, so there is a horizontal wire, right? So let us draw a horizontal wire like this. So there is a horizontal wire like this, got it? And it is falling like this, got it? Now it is falling like this. Uh, it is falling like this. A horizontal wire of a 10 meter extending from east to west is falling with the speed of 5 meter per second at a right angle to the horizontal. So right angle to the horizontal means, so let us suppose this is a right angle, so this is the right angle, right? So this is 90 degree, so this is the horizontal, so this is the 90 degree, right? Horizontal component of the earth magnetic field. So horizontal component of the earth magnetic field, so there is a lots of horizontal component of the earth's magnetic field like this, right? So there is in down also there is a horizontal component, in above there is a horizontal component. So what will happen? A direction of the magnetic field, so B is from what? South to north. South to north. Why south to north? Because it is the, see, they have geometrical south as well as north. They have not provided you magnetic south or north. So what will happen? Direction of the magnetic field will be in this direction. So let us mark it. So direction of magnetic field is in this direction. Got it? And the velocity or movement is this direction. See, it is moving in a downward. So, and this is, let us suppose this is a wire. So we need to find a induced current direction, right? So if you use right hand thumb rule, so direction of, so what will happen? So this, from this figure you can see that if you put, use your right hand, don't use your left hand. So this is the motion, means thumb, you have to use thumb here, just thumb, and this side you just put ring finger, and this side you have to pin as a middle finger. So you will observe that the direction, sorry, this side, this is your mid finger will show you the direction of current. So direction of current, so let us suppose this is your west and this is your east. So what will happen? Current will flow from east to west. Got it? Current will flow from east to west, right? Now next one is, next third part of this question, they have asked you which end of the wire is at a higher electric potential. Now this is very tricky question. Now we are thinking that the current is moving in this direction, right? So obviously this will be high potential and this will be low potential, but this is definitely wrong. Why this is wrong? So let us try to understand from the source. Now whenever you make a circuit like this, so let us suppose there is a bulb like this and there is a current source like this, right? Current source like this. Now current source like this, the thing is that you need to understand from here that when we are creating a current source, or where, from where the current will move, so see here, current will move. So let us suppose this is a negative and this is your positive, this is your high potential and this is your low potential. Now the outside current is moving from high potential to low potential, but inside you will always find that it will, when it is your source of current, when it is your source of current, so what will happen? It will, current will flow from low potential to high potential, current will flow from low potential to high potential. So low potential to high potential, so it means current is going from west to east. So which one will be have a higher potential? So current is moving from low potential to high potential, so our answer will be east direction. East will have high potential, right? High potential. I hope you have understood this one. So 6.6 question has been solved. Now let's go for next question, that is 6.6 6.7. 6.7. Now see, this is again one important question. First of all, read the question properly so that you can understand. Current in a circuit falls from 0.5 5 ampere to 0 ampere within a 0.1 second. If an average EMF of 200 volt is induced, give estimate self inductance of the circuit. Now self inductance, so let us suppose there is a circuit here and there is a cell source of power. So current, change in a current is how much? That is di is how much? What they have provided you, di is equal to 5 minus 0, that is equal to 5, right? And the time dt is how much? Dt is equal to 0.1 second, right? And EMF for this one is 200 volt. EMF is how much? 200 volt. Got it? Now for self inductance, so they are asking about self inductance. So for self inductance, which formula we are using? Self inductance, for self inductance what we use, E is equal to L di by dt. Now EMF they have provided use 200, L we don't know, di means 5, dt means 0.1. So by using this we will get L is equal to, just use this, 4 Henry. So I hope you have understood. Use this unit, H stand for Henry, right? So Henry is the standard unit of the inductance. So I hope you have understood this one. Now let's go and solve question number 6.8. Yeah. Question number 6.a. A pair of adjacent coil has a mutual inductance of 1.5 Henry. So they have given you pair of coil. So this is, suppose this is a coil like this. This is the coil, and there is another coil like this. There is another coil like this, or coil like this. Okay. Between them there is a mutual inductance, right? So they have given you mutual inductance, that is mu or M is equal to 1.5 Henry, right? If the current in one coil changes from 0 to 2 seconds, so change in current, how much? Change in current is equal to 20 minus 0. This will be 20 in the time period of how much? 0.5 second. What is the change in flux linkage with the other coil? So they are asking change in a flux for the other coil is how much? Got it? So how to handle this type of problem? So first of all, you know that how much EMF is being created, because EMF in both the coils will be same. So this will be equal to d phi by dt. Also we know that E is equal to mu. EMF is equal to mu or mutual inductance into di by dt. Got it? Now from this dt got cancelled out. So finally we can say that d phi is equal to m into di. So mutual inductance is 1.5 and to change in current is how much? Uh, change in current is 20. We don't require at all change in a time, so we can say that it is your 30 Weber. So I hope you have understood this one. So finally we have done almost or what? There is no question left. I hope you have understood this one. Thank you for watching. Let's subscribe the video so that we can continue give you continuous material. Thank you.